Hello, everyone, and welcome to our session. Today, we'll explore the intersection of advanced satellite technology, AWS cloud capabilities, and generative AI, and how this powerful combination is closing the data gap on natural disasters from space, enabling objective, data-driven decision-making that can save lives and protect communities. Space is a privileged vantage point to monitor our planet. Imagine a world where we are able to acquire and process satellite data in near real time, at scale, for early detection, monitoring, and mitigation of natural disasters. Sounds pretty good, right? Well, this is no longer just a vision. It's a reality that ICEYE is already delivering to their customers using AWS. But the story doesn't end there. What if we could further enhance these capabilities? Using generative AI, we can increase automation, augment the capabilities of engineering teams, and deliver higher quality insights about natural disasters even faster. My name is Nereida Guerra, and I'm a senior solutions architect in the aerospace and satellite team at AWS. Today, I'll be joined on stage by Andy Reid, Global Vice President of Government Solutions at ICEYE, and Steve Algieri, Senior Software Development Manager at AWS Space Team. Here's the agenda for the session. First, Andy will introduce us to ICEYE and how they are revolutionizing natural disaster monitoring and response. Then, I will be discussing how ICEYE is leveraging AWS service to architect their cloud-based workloads and solutions, implementing their end-to-end workflow in AWS and reducing latency. And finally, Steve will describe how his team, AWS Space, has been helping ICEYE to increase the efficiency and automation in their natural catastrophe solutions using generative AI models available via Amazon Bedrock. With that, I'll hand it over to Andy to tell us all about ICEYE.
Thanks, Nereida. All right, so I'm Andy Reid, VP of Global Government Solutions at ICEYE. ICEYE is an innovative space technology company, and I lead the part of the business that delivers our geospatial solutions to government agencies all over the world. We own and operate the largest constellation of synthetic aperture radar satellites, or SAR satellites, and we were the first company to miniaturize synthetic aperture radar. We've launched since 2018 more than 38 satellites, and we maintain a constellation, a very large constellation. And in 24 and 25, we'll more than double the size of that constellation. This means that we can revisit anywhere on Earth 6 to 10 times per day, or even more in some areas, with very high resolution. So SAR has been around for some time, synthetic aperture radar. The old approach was to build very complex, large satellites that required a lot of power to operate and cost billions to make and took years to build. They would deliver 10-meter resolution or lower at large scale and provide some value to the global stage. But they were very expensive and costly, and timing to build them was really a challenge. So governments or major corporations were the only ones who could access this technology. ICEYE's innovation is to build small satellites and miniaturize the synthetic aperture radar apparatus so that we can build satellites more quickly at a fraction of the cost. Our satellites are about the size of a dishwasher, and we can build one in 2 months. And now, at a fraction of the cost, we can maintain a constellation of dozens or even hundreds of satellites with top-class resolution at 25 centimeters with some of our collection modes. So we can democratize the data and bring this capability to radar image the world to a much broader community and deliver a lot of value. So what is SAR, for those that might not know? SAR is a radar imaging technology that can see through clouds, through smoke, through volcanic ash, and show what's happening on the ground with precise resolution. So you can see on the right side of this slide, an optical image or sensor might reflect back this cloud cover. However, on the left side, you can see the SAR image penetrates directly through the clouds and shows what's happening on the ground. This is a radar image. This is a radar image. So essentially, this is a radar image, so you can stack multiple images on top of each other and derive millimeter-level insights. So this is incredibly useful for the defense and intelligence community, but also for monitoring through the clouds what's happening during a natural disaster, or just understanding very specific changes to the Earth over time. At ICEYE, we're stratified into 3 segments. So we sell satellites or build, manufacture, and operate them for our clients. In our mission segment, this is largely focused on defense and intelligence use cases or other civil security use cases. The satellite data segment sells imagery to sophisticated radar image users all over the world. This, again, is largely focused on those defense and intelligence use cases. What makes ICEYE particularly unique is our solutions business, where we've invested in a very broad team of analytical expertise. We brought in more than 75 experts in geospatial and other technologies to essentially be customers of our own constellation, where we're collecting and imaging numerous different phenomena all over the world at once and providing geospatial, actionable data to our clients. So we're bringing in additional third-party data and analytics, fusing it all together to tell a story of what's happening during a flood event or a wildfire event. We developed this solutions business to democratize the data, to reach more of the world and help the world deal with global challenges. The global climate crisis is a great example. In 2023, 291 billion in economic losses were caused by disasters. 174 billion of those were uninsured, meaning those losses fell to the backs of governments, communities, or individual survivors, or even nonprofit entities. This is a massive increase from the 10-year average, and it shows us that more and more people will be affected by severe disaster suffering as time rolls forward. So in the US alone this year, more than $24 billion disasters. But this is a global challenge. The protection gap affects many people all around the world, and it's our goal to transform responsive recovery capability and at the same time help drive resilience. So the vision for our solutions business, we wanted to build a suite of products that could help our clients around the world understand the impacts before, during, and after the event. We started with a set of natural catastrophe perils. We have 4 products currently in the market, one being our flood solution, which we'll talk about at length here today, and lift the hood, if you will. The wildfire damage assessment solution, volcanic monitoring solution, and a wind damage assessment that's powered by change detection product that's in beta form as we speak. We're developing a whole additional suite of solutions across perils like earthquake, tsunami, landslide, deforestation, other critical infrastructure, persistent monitoring. But our natural catastrophe solutions are currently being used across the insurance market and government agencies all over the world. So a quick look at our flood solution, which we'll dig into more here in a moment. Imagine being able to follow the impacts, the depth and extent of water through the clouds for an entire hurricane event. Hurricane Ian, as it moved through Florida and then inland into the Carolinas and other areas, we were able to follow that and reflect that over 300,000 buildings had been impacted and to map the specific depth of that impact. This is something that has never been possible before and that can give real resolution as to what's happening during these events. Our wildfire damage assessment solution sees through the smoke to show where buildings have been burned and where they might have survived the fire. With the Lahaina fire in Maui in 2023, we were able to start collecting images within 3 hours of ignition and then tell the story that more than 1,500 buildings had been burned in the fire to our clients within 14 hours. We're developing an exciting product for clients in Brazil, where we'll help them monitor and understand through the cloud-covered areas in the Amazonia what's happening from a deforestation perspective. Using our dwell mode, we're able to spot and capture and see through the trees where settlements might be developing, Using other collects, we're able to see where roads, airstrips, or other infrastructure is being implemented. This means that when you can spot a settlement that's starting to be developed, you can possibly offset or mitigate the degradation activity, illegal mining, or deforestation that will take place. And we know that even mitigating a small fraction of some of the deforestation activity will have a very positive outcome on our climate. But jumping back to our Flood Insights solution. Flood Insights is an observation-driven analysis engine. This stitches together the full power of our constellation, as many images as we can get throughout the life of a flood event, with a very broad set of additional data sources to deliver to our clients the depth and extent of impact before it stops flooding. It starts with our operational forecasting team on the left side of this diagram. They're constantly monitoring global weather, and through an internal platform, they are using proprietary and open source models combined with over 50,000 tidal and river gauges around the world to determine where to make acquisitions at the right time. This platform allows us to capture as much images as possible. We're talking hundreds or even 1,000 images for a major event as it's unfolding. At the same time, there's an analysis team that is pulling together evidence from any possible source. So we're talking social media, news reports, aerial imagery, anything that can be located and brought in as a calibration point into our analysis. So this is thousands of additional data points that are brought in to our platform and analyzed. So potentially hundreds or even thousands of additional points there. This is all delineated over digital elevation models, and then the output is flood depth and extent in real time. This is built on our AWS architecture and even powered by AI, which Nareda and Steve will talk about quite a bit more here in the upcoming presentation. We deliver the first version of the analysis to our clients 24 hours after activation. So soon after the peak, we're able to show them the depth and the extent of the flood. We continue to refine that in the days following every 24 hours until all evidence is exhausted. With Hurricane Helene, an example of how this product makes an impact, we essentially were able to follow the impacts of that storm through the night as the storm hit Florida, inland and dropped torrential rainfall on a variety of different states, North Carolina, Tennessee, Georgia, and others, that were already saturated from precedent rainfall. It remained cloudy in those areas for 6 days following the event. So using traditional methods, airplanes or drones, essentially responders were flying blind. We worked with FEMA, several state agencies, several local agencies across the entirety of this event, and were able to provide them our insights as the event was happening, regardless of the cloud cover, regardless of nightfall. Our partners at Esri were able to get the data to Samaritan's Purse, a nonprofit organization, which was able, in the 72 hours following the event, to fly more than 60 helicopter missions to bring critical supplies, to see through the darkness, essentially, and bring critical supplies to people in need. In Australia, we have a whole of government relationship, and through the National Emergency Management Agency and Geoscience Australia, more than 50 agencies have access to Flood Insights, and it's a default response mechanism. One of the directors of analytics at one of those agencies drew this diagram for me at a visit last year, essentially showing that traditionally they start with about 5 or 10% understanding of what happened when the event occurs just after. Over time, using traditional flow of information, they're able to get to 90 to 95% understanding of what happened over the months following. With ICEYE in our Flood Insights solution, they start with 80% understanding of what happened and can get to 90 or 95% much quicker. This is a 16x increase in situational awareness and completely changes the trajectory of recovery for both the communities and the individual survivors affected. Altogether, since we started this solutions business, we've captured more than 250 floods around the world, more than 270 wildfires, numerous volcanic eruptions and events. We're capturing wind events now. The idea is that we can create a library of hazard impact information that can be incredibly valuable to inform the full disaster response life cycle. This is our goal, is to create a global source of truth that will help people understand better what's happening to our planet and better mitigate disasters. For example, A library of hundreds of flood events with structure-level impact information in Australia can better inform models and identify the trends and changes in risk that are occurring on the ground. It can also help with mitigation and risk reduction decisions. But with that, let's jump back to our Flood Insight solution, and I'll pass it back to Nareda to lift up the hood and talk a bit about how we're transforming satellite data into actionable insights.
Thank you, Andy. As you've seen, ICEYE is collecting satellite data and delivering customer value. In the middle, we have ICEYE's satellite data value chain. In the next slides, I will be focusing a bit more into how raw measurements coming from ICEYE satellite sensors are actually acquired, processed, and used to build these highly impactful NatCat solutions. And of course, I will be covering how this whole workflow is implemented in AWS. So it all starts with ICEYE's synthetic aperture radar sensors on board their satellites, capturing data and downlinking it to different ground station terminals present at multiple locations on Earth. At this point, ICEYE is receiving raw data in the form of data packets, including the payload data, but also communication headers and other necessary artifacts. In order to extract value from it, this data needs to undergo complex and computationally intensive processing. In the Earth observation industry, we typically use a series of levels to indicate the amount of processing that has been performed. Level 0 products correspond to the reconstructed and processed instrument and payload data and are the closest to raw data. Level 1 products incorporate geometric and radiometric calibration coefficients and georeferencing parameters that allow to adjust for how the sensors capture light and radiation, and also to add precise location data to each pixel. Level 2 products correspond to the derived geophysical variables of interest, like temperature or soil moisture. Of course, a storage of initial, intermediate, and final products is required throughout this workflow. The outputs of this processing, as you can see on the slide, are already much closer to what we typically envision when thinking about satellite imagery and Earth observation. However, ICEYE is not just a satellite imagery provider. They are a global solutions provider focusing on natural disasters. And in order to go from pixels to actual solutions, highly sophisticated data analytics and artificial intelligence workloads are required to fuse the satellite data with data from multiple other sources and extract meaningful insights from it. Inevitably, this whole workflow takes some time. For this particular application, deriving insights from natural disasters as they unravel, this time is highly critical. That's why reducing the time that each step in the workflow takes, including the transport time from the ground station antennas to a place where the data can be processed, and also minimizing processing and insight extraction time, is essential. Let's look now at how ICEYE has implemented this workflow in AWS and how this low latency requirement has impacted architecture design and AWS service selection. Again, we're starting with sensor data acquisition, and in this case, ICEYE uses AWS Ground Station to downlink their data. AWS Ground Station allows ICEYE to downlink their telemetry and payload data directly from their satellites to their AWS environment, and to uplink telecommands directly from their AWS environment to their satellites. They can book contacts with any of the 12 AWS Ground Station sites that are distributed all over the world, and they can do so by using the AWS Ground Station console, the AWS CLI, or the AWS SDK. This service uses a pay-as-you-go model per minute of utilization of the antenna, and removes the need for customers to buy, lease, or build their own ground station sites. With AWS Ground Station, the data is delivered directly to an S3 bucket or streamed to an EC2 instance in the customer's environment. transport time is greatly reduced thanks to the use of the AWS global network. In fact, for EC2 delivery, the time from ground station antenna to EC2 is under 200 milliseconds. Once this raw data is acquired, processing can start right away, and thanks to the breadth of AWS services, there is a lot of flexibility for you to choose the solution that best fits your needs, with ICEYE primarily leveraging Amazon EKS and Amazon EC2. Amazon EKS is a managed service that helps run Kubernetes clusters at scale and minimizes operational overhead thanks to the fact that it provides a fully managed, highly available Kubernetes control plane. Amazon EKS also offers a spectrum of deployment options from AWS managed to customer managed infrastructure so that companies can adapt to different sets of end user requirements. Using AWS for Earth observation has allowed ICEYE to have the flexibility to scale their compute on demand and be able to run the complex and computationally intensive algorithms required to process SAR data in a scalable and cost-optimized way. Regarding the storage layer, ICEYE uses Amazon S3 to store petabytes of data durably and cost-efficiently. Amazon RDS and Amazon Aurora are used to store metadata thanks to the fact that they support PostgreSQL database engine and extensions such as PostGIS. PostGIS extends the capabilities of the PostgreSQL relational database by adding support for storing, querying, and indexing geospatial data. This includes support for storing different types of spatial data, like points, lines, polygons, or multi-geometries in 2D and 3D. Other supported features are spatial indexing and spatial functions such as measuring distances and areas. Geocoding, so going from a physical address to a set of geographical coordinates, and reverse geocoding are also supported. Going back to the architecture, once we have this processed imagery, the next step is to use it in ICEYE's NatCat solutions, and for this, developing and implementing data analytics and artificial intelligence workloads is required. Amazon SageMaker helps us build, train, and deploy models that can perform, for instance, flat segmentation. This means detecting in a SAR image the area that is actually affected by a flat event. On top of all of this, ICEYE is not just covering one single natural disaster at one location. They need to cover more and more concurrent natural disasters occurring on multiple geographies, and they need to do so without compromising the time to insight. Therefore, scalability is key. And there are several elements to this scalability, one being having the right infrastructure in place, and another one related to be able to reduce the manual work and human in the loop required. As we will see later, Gen AI-based automation can be a great ally here. So this is ICEYE's architecture end-to-end at a high level. But of course, as you can imagine, there are lots of nuances and complexities to each of these elements, both on the technology side and on the people and processes side. That's why on the next slide, I would like to dive a bit deeper on the NatCat solutions architecture to cover aspects such as the variety of data sources that they are using and how they are actually closing the loop here so that the outputs of the NatCat solutions actually impact when and where their satellites are acquiring data. When it comes to the NatCat solutions, it all starts with event identification and impact assessment. For this, ICEYE has a meteorological forecasting team that is continuously tracking events and understanding when and where the biggest natural disasters are going to happen. Based on their findings, once an event is identified, these analysts send data requests, which translate into tasking their satellites to acquire data over the area of interest, and also trigger the collection of data from other sources, such as social media, weather data, or ground sensors like river gauges. One of the most interesting data sources here is social media. For this, ICEYE has a team that is continuously scanning content to identify especially multimedia data, so images and videos relevant to a particular event. They verify the validity of these data points, they geolocate them, and they extract insights from them, like the flood depth at a particular time, at a particular street in an area affected by a flood event. All of this information is then ingested into ICEYE's data processing and storage platform, being ultimately used in ICEYE's NatCat solutions platform that is hosted on an Amazon EKS cluster. Final aggregation, quality assessment, and report generation is done by a team of aggregation analysts that generate these final products for governments and insurers to understand the impact of the event. These outputs, together with feedback after the fact on how accurate ICEYE's assessments and predictions were, are fed back to the solutions for further improvement. And of course, algorithm and ML model development is continuously performed by ICEYE's large team of data scientists, ML engineers, and geospatial experts. In this sense, Amazon SageMaker helps create a collaborative environment where the different roles and personas can work together and build, train, and deploy models directly in a production-ready hosted environment. SageMaker offers a large set of tools and features covering the entire ML workflow, and it also eases the implementation of robust MLOps, thanks to features such as SageMaker pipelines. With SageMaker, you can use built-in algorithms, but you can also bring in your own script or even your own custom container just by pointing at the corresponding image stored in Amazon ECR. Finally, it also provides access to hundreds of pre-trained ML models that you can quickly deploy and start using in your applications. Let's look now at one of ICEYE's NatCat solutions called Flood Insights. We've established earlier that the time to customer value is highly critical. For ICEYE's Flood Insights, as soon as a flood event happens, within 24 hours, they provide a high accuracy, high resolution, depth, and extent map to their customers. And then as the event evolves, they keep updating this information. The more information that these customers and communities are given more quickly, the faster they can respond and react. And that's why ICEYE is continuously looking for ways to reduce the time it takes to perform each of the activities that you can see on the slide, from early detection to final report generation. What they identified is that even if they have the right AWS infrastructure in place, a significant part of these 24 hours was being spent doing manual work at different stages of this process. For instance, tasking analysts manually shift through multiple data sources to understand flood threat and impact. And then, based on this, they decide when and where to task data collection. Social media analysts, when tasked, scour through social media to find images and videos relevant for an event. However, manually finding, validating, and geolocating this data is time-consuming and resource-intensive. Finally, aggregation analysts generate and validate these customer reports, but again, interpreting, assessing, and summarizing this information requires significant time. In order to improve efficiency and speed up flood response, ICEYE has been working with AWS-based team to build an AI-based solution that can automate some of this manual work, allowing analysts to scale their work and ultimately accelerate the time to customer value. For the next part of the session, Steve will join to describe the solution that AWS-based team has built and some valuable lessons learned in the process.
Brilliant. Thanks, Nareda. As a prototyping team within AWS, it's been fantastic to see ICEYE's progress within AWS over the last decade. It's been especially impressive given the extent of AWS that they use on a day-to-day basis. especially when you consider some of their more cutting-edge technology, like synthetic aperture radar, that lets them see through clouds and smoke and help first responders get the right help to the right place at the right time. My name's Steve Algieri, and I'm the head of public sector prototyping and customer engineering. We're a dedicated AWS engineering team that works directly with customers to provide what we call art of the possible prototypes, with the aim of really unlocking a customer's hardest challenge and helping them move forward. The challenge that ICEYE set us was around their human specialists. So we have their social media experts who are scouring social media on an hourly basis, looking for evidence to check. We have their ICEYE analysts, so looking at that data to try and estimate flood depth. And then finally, the reporting specialists that pull all that data together to provide their customers with the insight that they need. The challenge that ICEYE set to PACE was, how can we assess flood extent automatically using generative AI? How can we do those first pass reports quickly under that 24-hour limit that the customers are demanding? And finally, can we explain the analysis? A big issue around generative AI to prove that what we're generating based on the data is truthful and accurate. Before we dive into the actual details, let's just have a look at the roadmap. The first thing we need to look at is our ETL pipeline, so our extract, transform, and load. So that's bringing in that social media data and doing that first pass processing on it. Next, we'll want to look at that generative AI usage. Can we detect the flood depth from metadata and pictures scoured from social media? And can we use other models to provide us with first pass geolocation? And finally, can we then pull all that data together within that generative AI through reporting? That was the challenge that was set. We're going to dive into the architecture a little bit and maybe look at a bit more details in how LLMs can be pulled together to solve this challenge. Let's start with a high-level architecture. So these are all of the systems that we pulled together as part of this prototype to try and prove that this could be done. The first thing we'll do is group these into two distinct areas. The first being social media data ingest and then secure product access. Let's look first at the social media. The first thing we're going to do is have ICEYE social media experts pull all that data into S3. S3 was the perfect choice for this. It's scalable, robust, and it can handle incredibly large files. Here also is the start of the automation by leveraging our Amazon Event Bridge. So automatically, as soon as a file is delivered to S3, we can trigger our Event Bridge, which in turn triggers our AWS glue job. And our glue job is our workflow. It's what's going to enable us to call both Bedrock for generative AI and SageMaker for that geolocation model. Once all of those elements have triggered and we have the LLM response, we have the geolocation response, all of that data is going to go back into S3. So effectively, we have a single source of truth for both the original files and the generated data. And that's our pipeline. Let's have a quick deep dive into how the language model, the large language model, would work in this example. So let's take two flood examples. The first thing we need to define is a prompt. So our prompt is going to set the context and the understanding for the LLM in order to understand how it's going to respond, the task it needs to do, and the format that it's going to reply in. Once we have that prompt and we pass both the prompt and the imagery to our LLM, so our multimodal model that can handle both text and imagery, we get that response back. In this case, we've asked for a flood depth in centimeters, but also, more importantly, for the later reporting, explainability. And the LLM will actually explain how it came to that depth estimate based on the imagery and metadata. The next part, if we jump back to our image, and let's put this back into context. The next part is providing access to that data to ICEYE's existing infrastructure. So the first thing we're going to do is provide access through our web application firewall. This is going to protect us from DDoS and other threats on the internet, and it's going to pass through into our AWS, our Amazon API gateway. The gateway is going to act as our single source of entry to the data, and we're going to leverage Amazon Cognito. In this case, because it's a prototype, we use dedicated accounts, but the benefit of using Cognito is it can subsequently be extended to other sign-on, such as single sign-on, and integrated into existing systems. Our API gateway is going to leverage our Lambda infrastructure, so our serverless infrastructure to access the data. And that in itself is going to access Amazon Athena. Now, the choice of Athena was based on keeping all of that data in S3. Athena allows us to query the data and the generated data in place without requiring a separate RDS or other instance. So everything's kept together. Let's pop that back into the main architecture. So the last thing to do is then connect our Athena instance to our S3 bucket. And we're done. So we now have a secure pipeline for our social media data, together with our Bedrock and SageMaker instances running concurrently on that data automatically as soon as something comes in. We then have our secure product access, which can be extended to ICEYE's other data lakes within AWS once that data is ready for sharing. So let's have a look in terms of one of the questions we get asked a lot is how easy or how simple is it to bring generative AI into your product suite? And the answer is, thankfully, we've made a complex process as simple as possible through Bedrock. Let's use our social media ingest platform as an example. So the first thing we need to do is provide access to both Bedrock and the S3 data so they can work together and that data can be shared. That's as simple as defining a CDK construct, in this case, and simply defining the model that we want to use. So in this case, we used Claude 3 from Anthropic, and then defining the use of that model in terms of an invoke command into our S3 workflow. That's it. S3 and Bedrock can now work together. The next stage is how do we prompt? So we talked about the prompts before, so set context, task, and format. And then the next stage is to invoke it. And that's as simple as defining our standard AWS runtime and calling with a single command the Bedrock invoke method to provide the prompt and the imagery, importantly, that we want that LLM to work on. And it's as simple as that command. And from there, we get our response. So in less than 10 lines of code, we've defined access for Bedrock and S3. We've defined our prompt, our invocation, and we've got a result. So as a public sector prototype and customer engineering team, we are focused on these incredibly hard challenges. We help our customers to understand the challenge that they want to solve and then provide code, working prototypes that solve that challenge. So if it's a challenge that maybe you're facing that you need help with as a customer-facing team, you can get access to an AWS engineering team. So I'd like to call up Andy and Nareda for some final comments. Nareda, I'll start with you. You've obviously been working with a number of Earth observation customers. What are the common challenges that they've been facing?
So Earth observation companies face a multifaceted challenge. They're not just dealing with the complex technical problem of building and managing a satellite constellation. They need to process vast amounts of data and deliver the final products to their customers all over the world as fast as possible without compromising on quality. AWS allows these companies to implement an integrated architecture that covers their end-to-end workflow. And one of the particularities is that AWS has designed features and even services specifically developed for these use cases. AWS Ground Station is a prime example of this, allowing ICEYE to downlink their data directly into their environment and reducing transport time thanks to the use of the AWS Global Backbone. I would say this cloud-native approach allows companies to focus more of their time on innovating on their products rather than managing IT infrastructure, and it empowers them to incorporate new technologies such as generative AI as they emerge. And really, for ICEYE in particular, they've gone beyond acquiring and selling satellite imagery. They're using data analytics and AI in AWS to solve real challenging problems. So this is really a great example of how Earth observation can have a positive and tangible impact in the world.
Amazing, thanks. Andy, ICEYE has been on an incredible journey with AWS. For you as a company and a cloud-centric approach, how has that impacted your operations?
Yeah, I mean, I think we've touched on so many of these pieces here, but time to insight is essential for us. And we're dealing with such vast amounts of data, whether it's from the imagery to the other stuff that we're harvesting. And being able to see through the noise and reduce that time to insight has been absolutely essential. And so the AWS architecture that we have is not only critical to today's set of solutions, but in the future, as we look at more perils and we have many, many more satellites and we have many, many other third-party data sets that we're pulling in to look at the world in this way, I think it's going to be absolutely critical for us to continue building that out.
Awesome. Thank you. So it's been awesome to hear about ICEYE's progress on AWS. Thank you all for joining us. Please do take a moment to provide your feedback on this session. It really does help us improve and bring you interesting sessions next time. We'll be available after the session if anyone would like to come and have a conversation about what they've heard today. But otherwise, thank you for listening, and we look forward to speaking to you. Thanks.
Thank you.